If you were a user of XP back in the day, or you just use it for fun occasionally like me, you will probably find yourself eventually diving into the Windows folder. Just check out what's going on in here. And if you do this, you're gonna find a lot of interesting stuff. Like you're gonna find the wallpapers, you can even find Bliss in here, and the default 20. You can find like the screensavers. You can run your pipes straight from the Windows directory, so you can find all sorts of neat things. But even if you spend an infinite amount of time in here, you're never gonna find certain things. Like if I were to go open up Paint, and I draw a little bit, and I try to close this image right here, this warning icon, you're never gonna find that. Where's the image for this? There's no warning icon.bmp hanging out anywhere. You're never gonna find the icon for this close button, or for these dialog buttons, or for the start menu, or for the thing that I got really interested in recently. We restart the machine here. This. Where's this? We can find the wallpapers, you can find all sorts of screensavers. Where's that image? You want to talk about Bliss being the most viewed image in the world. At least you could change Bliss if you wanted. You can't change that boot screen. You were looking at that every single time you started your computer, whether you liked it or not. So where is it? And I recently was pondering this question. And as a kid, I would never be able to figure that out. Because if it wasn't just a file in the Windows directory, I probably wasn't going to find it. But I've grown up and I've gotten a little bit smarter. I've learned a couple more things about how computers work. And maybe I know enough to be dangerous. And thinking about this, if I could do that for Windows XP, could I do that for every version of Windows? What would be the differences? Which ones would be more complicated than the other ones? Could I create a master document that has instructions and descriptions of how every single boot screen out there works? Could I do that? I had an interesting journey, and what I want to do today is just take you through that. So let me take you back to 1985. When the very, very first version of Windows came out. Okay, so we're in DOS, and since this is just a shell on top of DOS... Oh, that's not right. Windows. Since this is just a shell on top of... God damn! Since this is just a shell on top of DOS, we start it from DOS by typing in Win. And don't blink, because this is going to go really, really fast. Alright, did you catch that? That was our very first boot screen ever. Probably get some help from the edit here to freeze that and let you look at it. But yeah, it looks pretty good, I guess, for a first boot screen ever. You can tell that quite a bit of it is just regular text mode rendering. But there is a graphic in there. The Microsoft logo is obviously some kind of graphic. It's got that drawn feel to it, drawn by someone not over the age of 10. But the question is now, where do we find it? Like, how do we actually get our hands on where that is? This is the Windows 1.0 Windows folder. It's very small. As you can see, it's only 30 items, and they all fit on screen on my 1920 by 1080 monitor. And just like in modern versions of Windows, there is no Microsoft logo.bmp or anything obvious in here. There's no individual file. So we know that we have an image somewhere in one of these files, but we don't know what it is, and we kind of don't know what we're even looking for, right? Because all of these files, ultimately, if we pop them open in a hex editor or something, they're all just a bunch of bytes. How do we know that what we're looking at in here is an image? Like, how do we know what this is? Is this just code? Is it, like, what is this? Right? How do we know that we found an image in here? Now remember, this is 1985 we're talking about here. This is not exactly cutting-edge technology. So I'm going to bet that whatever method they used probably going to be the simplest possible way you could store an image, and that's a bitmap. Promise this is the only time I'm going to break out the whiteboard in this video, but I do want to make sure we're on the same page, because I do think this first step is kind of important and interesting. So I'm going to make a little image here, and just for the sake of simplicity, we're just going to assume that every image is a rectangular grid of pixels, and each pixel has one color. Okay, so we've got this Rubik's Cube looking thing. We have some arbitrary rectangular grid of pixels, and we want to encode this into a computer somehow. And computers, the only thing they can really do is work with numbers. So we basically need to find a way to turn this grid of colors into a list of numbers. It's effectively our task here. So if you were just coming up with a way to do this, you might think of the fairly obvious strategy, which is, let's start by just associating every color with a number. So we could say that the number 1, for example, is the color red, and the number 2 is the color orange, and the number 3 is the color blue. And once we have this color table, well, all we need to do is read the pixels of this image in some order, and the natural order is read them left to right and top to bottom, like we were reading English text. It's just the most natural thing for us to think about. Then all we need to do is just put down the number that associates to each color in the order that we read it here. So we start at the top left with a red, so that's going to be a 1. And then we get a blue, so that's a 3. And then another red, so we get a 1. And then just continue doing that in the order that we defined. And so we have this sequence of numbers, sequence of bytes basically, that corresponds to our image. And if we have a program that understands this color table, that knows what our color table is and knows what our reading direction is, then that program can perfectly recreate this image from these numbers. And what we've effectively done is invented the bitmap. This is pretty much the simplest way you could store an image. And I'm betting you that this is how they are storing these graphics. Okay, so if we're going to assume that it's using this strategy to store the Windows logo, then how does that help us? Well, I want to show you something. If we go into System32 and we look for calc.exe and we open this in Notepad, you're going to notice a lot of weird shit going on, because basically what we're doing is interpreting the bytes of this program, which are not text data, as if they were text data. And you'll notice that even some things that are text data that are embedded into this program, they read perfectly fine. They're just kind of in the middle of a bunch of nonsense. Like, you can read a few actual words in here. Now, if we keep scrolling down through this, who knows what data this actually is? It's all weird stuff. It might be code. There's a bunch of text in here. We don't really know what this is, but some of it clearly has a pattern, right? Now, if I maybe decrease the text size, and I kind of fiddle with the size of this window a little bit, you might start seeing something in there, and you're not crazy if you do see something. It turns out that when you have a bitmap, a really cool property of bitmaps is that the data that you end up with, the string of numbers, it resembles the image itself. In fact, if we go back to our example, and I stack these numbers, where we have a red thing, we have a 1. Where we have a blue thing, we have a 3, right? Like, it mirrors, the structure is the same. So using this technique here, I think we can actually locate the Windows bitmap if we just, effectively open every file in the Windows folder with Notepad. So at this point, that's what I could have done, right? I could have just started opening all these with Notepad. However, I assumed that maybe we were going to need something a little bit more robust, because as you saw there, Notepad is pretty ugly to look at. It's possible that I might miss something if I was just relying on that. So I kind of wanted something that was a little bit more robust and maybe made searching for patterns slightly easier. So what I did is I put a few brain cells together and I made a program that would do what I'm looking for a little bit more directly. So this little tool that I wrote is going to be able to take any file, and let's just throw in Notepad, for example, and it's going to show us the bytes of Notepad, but interpret them as if they were the data for some imaginary bitmap. Now, just like opening stuff in Notepad, we're going to see a lot of gibberish, basically, because the vast majority of the data in here is not image data, right? It's just code, or it's text, or it's something else that makes no sense when interpreted as an image. But certain parts of it might start making patterns. And if they make a convincing enough pattern, that is a sign that the underlying data actually does represent an image. So, once I had built this, I was looking at this list of files here in the Windows folder, thinking, you know, if I was a bitmap for the boot graphic, where would I be hiding? And there's not a lot of files in here that would even suggest that a bitmap would be in them. Like, for example, like a font file. Like, is the boot graphic really going to be in a font file? But might it be in, I don't know, win.com? I mean, this is the thing that you run when you want to start Windows, right? So it seems like a pretty safe bet it might be in there. So let's check it out. Now let's see here. We've got something kind of interesting going on. Let's maybe switch it to 1 bit per pixel. And yeah, the bottom of this file, you know, there's kind of a pattern in there. And as we move around the width here, there's something sort of materializing into existence down there. I don't know if you, yeah, that looks a little interesting, doesn't it? Maybe we can get it even better. Yeah, I think that's actually pretty conclusive. Our little educated guess worked. This is, in fact, where the data is. So we've managed to locate where we think our bitmap is. It's in win.com. It's roughly at the end of the file, it looks like. So now what we have the privilege of doing is popping our file into a hex editor and staring at it really hard. So at this point, you know, we just kind of do a long series of educated guessing. Like, we notice that there's a bunch of random data that just abruptly kind of ends here and starts with zeros. So this is probably where it starts. It looks like it probably goes all the way down to the end of the file. And, you know, you just do a bunch of guessing like that. Try to maybe reconstruct the bitmap from this data using the algorithm that you think it's using. A lot of boring shit that I'm not going to go into in this video. That's for the Google Doc that's in the description that actually does describe exactly how this format works. I was able to figure it out, and to prove that I was able to figure it out, I was able to put together a script. So here I have a Python script that will take an image that I make of the right size and the right colors, and it will turn it into the format that is expected by this file. So I was able to draw my own little replacement Windows boot screen and put it through this script, and the result is my own custom boot screen for the shittiest version of Windows ever. So here we are in DOS. We'll go to the Windows directory and run win. And again, don't blink, because it'll go very fast, but if you look closely, nice. That's what I'm talking about. So we did it. We actually figured it out. I'm excited. Like, this is actually starting to go somewhere already. So let's keep our momentum up, right? Let's just move straight along to the next version of Windows, which would be Windows 2. Windows 1 was so good. Why not make Windows 2? Okay, this is going to look really familiar. We switch to the C drive, we go into the Windows directory and type win. And this is going to be a little bit slower, but still don't blink. Now, if you thought that I just ran Windows 1 again, I don't blame you, because that was almost the exact same thing. So here's the Windows 2 Windows directory, and you can see it has 2 extra files in it compared to the Windows 1 directory. And let's just open up win.com from Windows 2.0. And you notice win.com is actually quite a bit bigger, but just like before, the Microsoft logo is right there at the end of the file. So yeah, everything is exactly the same. And what that means is I just drew like a slightly updated version of it, ran it through the exact same script that I had before, and we can see what that result looks like in just a second. Let's boot Windows. Yeah, looks good to me, right? No need to put in a bunch of more effort when Microsoft wouldn't even put in a bunch of more effort to make their boot screen look any different. So there you go. Those are the 2 DOS shell versions of Windows. We managed to figure them out. Now things are, of course, only going to get more complicated, so let's see if we can keep up. How well will we do when faced with Windows 3? So this part in DOS is going to look pretty familiar, but let's just go ahead and run Windows and take a look at our boot screen. Alright, so that was significantly different. We've dropped the big blue background with text on it in favor of what looks like just a full, complete image. With color in it, too. How crazy. So, we've upgraded quite a bit. Alright, so here's the disk for our Windows 3 installation, and there's already quite a bit more going on. That's a lot of files compared to the previous versions of Windows. However, we do still have a win.com, so why don't we just throw it in here and see if that image is somehow stuck at the end again. And... well, there's some kind of pattern in there, but yeah, it doesn't really look directly like an image anymore. We can try some different formats, but I mean, it does sort of look like there's something going on, but that's not obvious at all. I mean, this is the only reasonable place, considering all the other files, that this bitmap could even be hiding. Right? There's something happening. What is it when you have semi-structured data that you suspect is like an image? Well, I start worrying at this point that we're looking at a compressed image, which makes a lot of sense, because this is still deep in the infancy of personal computing, at least relatively speaking. Hard disk space at this point is still at a premium. I mean, you can't even really assume that a computer is going to even have a hard drive in it. Some people are still running Windows 1 and 2 off of floppies. So we really don't want our bitmap to take up a lot of space on the disk. And this is pretty scary because, well, what compression method did they use? Who knows? But if we get lucky, there's actually something that we can do to work with this. I want to just take a brief segue into a Wikipedia article I've been to a hell of a lot over the course of this project for the BMP file format. And it's surprisingly complicated for what a bitmap actually is. You know, the idea, of course, is quite simple, but there's a lot of stuff you can add to it. But the only thing I'm interested in is 2 things. First of all, the file header. So every bitmap file is going to start with the same 2 bytes. It's going to start with bytes that read BM in ASCII, 424D. And if we scroll down a little bit here, the compression method being used. So these .bmp files, they actually support basic compression methods. The most common ones by far are these run length encoding sort of things. I'm not enough of a compression guru to look at this and say, oh yeah, that's definitely run length encoded, but we can pretty easily find out, because we know bitmap files always start with these 2 bytes. And if those 2 bytes are still in there, that's a pretty good sign that what we're looking at is just a bitmap file that they've stuck in there. Just to sort of illustrate what I'm talking about, let's go ahead and save this file that I made as a bitmap. So we'll drag our BMP over here, and you can see, as expected, it does start with BM. or 424D. Let's open up our Windows folder and see if we can find the letters BM in there anywhere. So let's open it up, BM. And okay, wouldn't you know it, there's a hit. And wouldn't you know it, it seems to be right at the start of our suspicious looking data. And we can sort of visually see that, like, for example, if you look at this line, you'll notice that we have like an open parenthesis right here near the end of it. And you can see it actually is the same on our example bitmap. This is, I believe, the version of the bitmap header or something like that. So I think it looks pretty safe to bet that this might just be a bitmap file, a BMP file, that's been tacked onto the end. So let's do this. Let's take this data just all the way to the end of the file, make a new file, paste it in, and save it. Windows 3.bmp. And let's take a look at it. What do you know? It already has a preview because it's just a BMP file. We kind of got a little bit stuck there, but using a bit of luck that they did just use a regular BMP file, we were able to get there. So now that we have a regular old bitmap file, we can just edit it with any regular image editor, kind of draw on it, and then in theory, right, we could replace this bitmap with the one that's at the end of win.com, and we would have, you know, totally custom boot screen for Windows 3. Now there are a lot of caveats with doing that. I've found that GIMP tends to be the best for this kind of thing. You can see that GIMP is actually very respectful of the way that the bitmap is. Like, you can see it actually shows us and recognizes the color table, the exact color table that's being used. So if I like draw on it, you'll see that it's not actually introducing any new colors. Like, the edges of this brush are being sort of anti-aliased using the colors that are actually available in the bitmap. And GIMP also has the option, if we export this as like, again, new.bmp, it has the option to not write color space information, which ends up exporting as like an earlier bitmap format that Windows 3 actually knows how to work with. With all this in mind, the first bitmap I decided to draw was basically just using the exact same colors at the exact same resolution and seeing if that would work. Well, let's take a look at the result of that. Alright, now we're in DOS. We're going to go to Windows and run Win, and yeah, it works. So as long as you are attentive to the bitmap format, it ends up working out just fine. So once you know that you can do that, the next question that I naturally had was, what are the limits of this? Can we actually change the colors or the resolution of the image that we're saving? So I actually went and I made a couple other versions. For example, this one here. This one uses a different set of 16 colors. You may have noticed, if I go back and I open up this one in GIMP again, if you look at the color table, there are a total of 16 colors, but the first 8 or even 9 of them are all black. So in here, I used a totally different set of 16 colors. There's still only 16 of them. And you'll notice I even bumped the resolution up a little bit. So this image is slightly bigger than the original. And I was curious, you know, if this was okay. Alright, so here we are in DOS again. Let's go Windows and Win and Moment of Truth. Take a look at that. It actually still works. So the Windows 3 bitmap is surprisingly flexible. You can only use 16 colors, but you can use any 16 colors you want, not just the weirdly disgusting distribution of 8 colors that they give you, and you can even change the resolution if you want. So yeah, 3 versions of Windows down, and we haven't really encountered that much resistance. All of it has been relatively simple. Let's just hope it stays that way for a little bit longer. Alright, moving on up. We've already run into Windows 95. And this is definitely my personal favorite boot screen. We don't even have to boot into DOS anymore. We're just going to go straight into 95. And that is just, in my opinion, perfection. So Windows 95 is obviously one of the most beloved versions of Windows ever, and for that reason, it does kind of have a critical mass of nerd, which means that if you have been in retro Windows circles before, you might actually already know the trick for this. So if I just go into the C drive here, I've got a file in here called logo.sys, and I got this one off the internet. The idea is that if you put a bitmap with a particular format into the root of the C drive and you call it logo.sys, Windows will actually use that bitmap instead of the default one. So if I open this up with Paint, I should be able to see it. Yeah, so it's sort of this ZX Spectrum inspired boot screen, which looks pretty neat. And if we reboot the machine with it called logo.sys, yeah, there we go. Pretty neat, right? It's even all fancy and animated and everything. Pretty cool. But that's not really what we're after in this project, right? Windows is specifically looking for a file called logo.sys, and if it sees one, it's going to use it instead of the default. But that doesn't answer the question of where is the default one, and how do we replace it? So here I have the Windows 95 disk image. A lot of stuff going on, but we also still have a win.com. So where do you think we're going first? Yeah, we're going to check out win.com. And we're not actually super confident that we're going to find a bitmap necessarily. And we don't. Yeah, that just looks like a lot of random cruft. Well, we're going to go ahead and pop open win.com in a hex editor and just search for BM again. See if maybe we can find that bitmap header. Well, there is a BM, but usually with that bitmap header we get a bunch of zeros in here and then a parenthesis at a certain point. We do have a parenthesis, but it just doesn't look like a bitmap header. Can we continue searching for it? Let's find again. Nope, that's it. So that's the only one. Huh. Maybe they really have moved it out of win.com. Who knows? Now, of course, this is where I sort of start digging through anything else that even remotely looks like it might be boot related. You can find some interesting things, like you can find logo W and logo S.sys just sitting in here in the Windows folder. And if you open these, you can see that these are bitmaps here, but they're the bitmaps for the shutdown screen. So these are pretty interesting, but these are just for shutdown, and I could edit these and it would show up on the shutdown screen, but I'm not really interested in that. I want the boot screen. You know, I spent a really long time looking for this, probably several days, just looking at anything that had anything to do with logo.sys, any bitmap files anywhere, just searching the entire disk for bitmap headers. I even looked on the install disks to see if I could figure out like where it was copied from the installer. I couldn't find anything. It was like Windows was intentionally going out of its way to hide it from me. So at a certain point, I just had to wave the white flag, right? Like, I obviously can't figure this out. So I did decide eventually to just give up and Google it. Now here's the twist. It turns out that actually not even Google knows where this bitmap is. So if you search for information on the Windows 95 boot screen, 99% of what you're going to see is people saying to use the logo.sys trick. Of course, like, why would you want to do anything else? That's a perfectly fine way, and the expected way, the supported way, to replace the boot screen. But if you look for information on where actually is it, there's not much. On BetaWiki, which has this great article, which I did not read anything other than this part, they actually just say, the main boot logo is contained in io.sys in a compressed form. When they say it's stored in a compressed form in this file, they're not talking about regular BM, bitmap run length encoding compression. If we search this file for the BM header, we can find a few BMs, but they're all like part of text or they're just kind of random. They're talking about a custom proprietary form of compression. And that's what I was afraid of in Windows 3. And if you continue looking for information, You will not find details about this algorithm anywhere. At least I didn't. There's even a Wikipedia article about this, but they have nothing of interest to say. You will eventually run into a forum post on MSFN from somebody trying to do the exact same thing. They want to know how to extract that bitmap that's in io.sys. They get a bunch of back and forth, which is kind of debatably useful. This guy, R-Low, eventually says at some point that he has done it, and he knows how to do it. He knows. This guy knows how to do it. But his response to people begging him to give up the secret results in him saying this: "I see nothing especially fair about that. I consider it one of my trade secrets." So this dude is not spilling the beans. That leaves me in an interesting position. It looks an awful lot like there are very few people that know how to do this. And it sounds also like I could figure it out by examining this file and like reverse engineering it. But am I really qualified to do that? I don't think so. So as it stands, we don't really have much of a shot of uncovering the original one, which is a shame, but fortunately we do have a lot of information about how logo.sys works, because a lot of people have made them. This is where the nerd critical mass has been focused. I mean, Wikipedia's got all this information on how logo.sys works. So I think we can still make a nice looking bitmap and sort of technically replace it by using the logo.sys trick. And that's what I went ahead and did. What I want to point out here is 256 colors, first of all, is a lot. This image actually looks pretty slick, even at 256 colors. Looks nice. This color table over here sort of also reveals how the animation worked. So if you remember, the original boot screen had a fancy, slick little animation. I originally assumed that that loading bar, those spinning colors, was done by some other routine, and it wasn't actually like part of the bitmap, but it turns out that it is. So you'll notice the very last few colors in the color table for this bitmap are these pinks that make up the central logo here. And it turns out that the last few colors in the color table are actually cycled through at runtime. And this is how people are creating these animations. All they do is just color the parts they want to animate in the last colors of the color table. And it's so customizable, in fact, that you can actually choose how many of these colors are actually the ones that cycle through. So by default, I think it's about 20. The last 20 colors of the bitmap get cycled through. In this case, I think I needed something more like just 10. So I was actually able to change that in the bitmap file itself and define how many colors I wanted it to cycle through, which is all really cool. I mean, there's a incredible amount of customization here that you just do by fiddling with numbers in the bitmap. And once again, GIMP is like the MVP for doing stuff like this. So there is a dialog you can pop up in GIMP. If you go here to map rearrange color map, you can choose exactly where all the colors of your color map are, which in this case is important. But yeah, all of that works out, and I can even show that to you. And let's see it. Now, doesn't that look nice? Not quite perfect, but I think it looks pretty slick, and I'm happy with it. So yeah, I'll be honest, the fact that we can't gaze upon the true Windows 95 boot screen is pretty disappointing. We may as well just not think about that too much and move on. So following up the much beloved Windows 95 was the possibly even more beloved Windows 98. And we'll take a quick look at what our boot screen looks like in 98. Oh, it's going to be pretty similar because overall 95 and 98 were fairly similar operating systems. And as you can see, not a huge amount of difference. And I will just go ahead and let you know now to save us both a bunch of time. They are exactly the same. The details about how the boot screens work are identical between 95 and 98. There is still a bitmap that cannot be comprehended by mortals, stuck in io.sys somewhere. And there is still a logo.sys trick you can use to bypass that and put in your own boot screen. But yeah, it's the same, so we can move on. Now, following up, the much beloved Windows 98 was the much maligned Windows ME. And we know that ME and 98 are pretty similar too, so I was expecting the situation was going to be basically exactly the same. They've changed the design of the boot screen quite a bit, but it probably still works in about the same way. We can discover that the logo.sys trick does still work, but interestingly, the io.sys situation is actually a little bit different, and this is something that our low guy from the MSFN post was actually alluding to. Let's throw that into our hex editor and just take a quick look at it. And, you know, as we scroll through this, it's not super obvious, but there's something that feels very different about it. So an example of that is here in the Windows 95 io.sys, there's like a bit more instances of patterns, right? Like there's a bunch of just repeated Fs in here, there's a big space of zeros. Yeah, like here's a bunch of text, right? So as we scroll through this, we can see a bunch of different things. If we look at Windows ME's io.sys though, it's kind of just a bunch of garbage the whole way through. Something that Arlo did feel like sharing with us is that this is because the entirety of Windows ME's io.sys is compressed, or at least almost the whole thing. Whereas over here, this io.sys is actually not entirely compressed, it's just the bitmap, wherever that is. Our good friend Arlo, whose real name is Rudolph, this guy was a paragon of Windows 95, 98, and ME modding, and he actually made a tool that does decompress the Windows ME version of io.sys. So here's another copy of an ME disk where I actually ran Rudolph's tool, and I have an io.original.sys, which is the original compressed version, and the io.sys, which is decompressed. And if we put this in here, we got a bitmap header in there? Let's search for VM. Why not, right? There's a few false positives, but what about this? That one looks pretty good. This does look like bitmap data, doesn't it? So, yeah. It turns out that with the help of Rudolph's tool, we actually can extract the bitmap. But what's really interesting is that Windows ME will actually continue to read the uncompressed version. You don't even need to recompress it. Once you decompress it and you replace the bitmap, do whatever you want with this file, it'll just read it. So all you need to do is rename or hide the original io.sys and everything will work just fine. So I went ahead and I made a boot screen with about as much effort as I think Windows ME deserves. So let's just take a quick look at that. Yep, that looks pretty good. I even broke the animation in it, so it's got extra effort. Now this, of course, is raising some questions. Is it possible that the algorithms used for the Windows ME version of io.sys and the algorithms used to compress just the bitmap in the 95 and 98 versions of io.sys, are they the same? Now, unfortunately, you cannot just run the io8 decomp thingy on those 95 and 98 io.syses. It just doesn't work, but it makes me wonder. Unfortunately, it turns out that Rudolph's io8 decomp tool here is not open source because, well, that just wouldn't help him maintain those trade secrets now, would it? But I did a little bit more Googling about Windows ME in particular instead of 95 and 98, and I came across something. There's a post on the Retrocomputing Stack Exchange about disassembling io.sys. And as is typical for Stack Exchange, somebody who is, you know, more knowledgeable than maybe anyone else in the world about the particular question being asked comes in here and dumps the most helpful information I have ever read on this subject by quite a few orders of magnitude. Down here, the compression format itself is a rather unremarkable LZSS-ish bitstream split into chunks. Rudolph Lowe's io8 decomp can decompress the file in place, or you may see how grub4dos accomplishes it. And that's a link. And guess what that's a link to? That's right, that's a link to some code. So there's a whole routine in here which does exactly what it just said. All of this code here that's highlighted in yellow is the decompression routine for the Windows meio.sys. This is it. Additionally, there's this little footnote here, right? Okay, so let's go read that footnote. As it turns out, this compression format was only slightly altered from the one used to store the embedded boot up splash screen in earlier versions of Windows. Alright, so the first thing that I wanted to do here was I wanted to verify that this algorithm actually works. And the way that I decided to do that was just do it on paper, like I'm in a first year data science and algorithms course. So I do it, I get the bytes out for the compressed Windows meio.sys, I start working on it, I read through it, it takes me quite a bit to sort of understand what's going on here, and I do it on paper, and I can verify that the same bytes came out the other end as that came out through Rudolph's decompressor. The next thing that I do was take what I think is the compressed part of the Windows 95 io.sys and try this algorithm on it. And I get 2 bytes out with my work. And you want to guess what those 2 bytes were. And now I really know where the next week of my life is gonna end up. So what I could have done is download this C code and make like a surrogate C program that just runs these functions on some data that I throw into it. I could have done that, but I was not super confident that was the right thing to do, because the guy said literally that the algorithms were not exactly the same, which means it probably wouldn't have worked. And if it didn't work, then how was I going to figure out what was wrong? With that in mind, I decided to re-implement it in my own code. Like, I'm not focused on anything else at this point. Fuck whatever else is going on in my life right now. I need to do this. This is the most important thing that has ever happened to me. I sit down and I focus, and it takes me a couple days, and I make a lot of mistakes. Generally understanding the algorithm was kind of a struggle. Now, I did get some cool stuff out of it. Some of the incomplete, not quite correct versions of my algorithms made some pretty cool glitch art. And, you know, when you see something like this, it hurts, of course, knowing that you didn't quite get it right, but it's also really, really cool because you know you're on the right track. And you can even use like some of the ways in which this messed up as like hints to tell you what might have been wrong. It was a pretty long process to get a decompressor that actually did work. Lots of mistakes, lots of trial and error, but at the end of the day, after that effort, it pays off. Because look what I end up with. That's it! That's the boot screen. This is the exact set of bytes that made up this original image. Crazy. Now, I'm sitting here after, you know, a few days, maybe a week's worth of work, sitting here like, man, I did it. But we're only halfway done, actually, because I want to replace this. What I need to do at this point is write a compressor that goes the other direction. Now I need to have something that turns uncompressed data into compressed data so that I can actually replace the thing. This part was harder because I don't have anything to guide my implementation. The grub for DOS code only implements a decompressor. So I need to use what I've learned about the algorithm, and I thought that I completely 100% understood the algorithm at this point. I didn't. So a long process, a really long process of trial and error, trying to make sense of this when there's no information anywhere about it, there's just that C code. It was difficult, but it was very, very fun, and I got it to work. And that is truly a replaced Windows 95 bitmap. So at the end of the day here, what I have is not only a completely working compressor and decompressor, but also a full and complete description of how the algorithm works for compressing and decompressing, and how all the data structures actually behave. Why keep this to myself? Because I couldn't find this information anywhere on the internet, so here it is now. I put this stuff up on GitHub. It starts with a huge comment that describes exactly, in as much detail as I possibly could, how this stuff works. I think it deserves to be somewhere on the internet. It's possible someone else has done this and written up something about how this algorithm works, but I couldn't find it. Also, I gotta give a shout out to whoever the heck Bean is, the anonymous person that is credited with writing this code. Whoever you are, wherever you are, thank you. You have no idea what this means to me. Well, that was definitely the most unexpected place that this project brought me. But it's also a very appropriate way to bookend the first sort of era of Windows. Everything we've been looking at so far has been DOS-based in some way, had DOS at its core. Now we have an opportunity to move on to the NT-based family of Windows. I decided to start with Windows 2000. If you've been a long-time viewer of the channel, you will recognize this screen. Yes, it's true, I have replaced this in the past, so I do already know how this one works. So here we are in the disk for our Windows 2000 machine. I want to introduce you to a tool that is more and more relevant as we get closer and closer to modern Windows, and that's Resource Hacker. Windows executables have a standard format for storing resources that they may want to use. Lots of things are resources, lots of things can be resources, and also lots of things don't have to be resources, but this is a very common way to store images, sounds, text, other stuff in the file. And since it's a standard format, tools like Resource Hacker know how to parse it and understand it and can show you the results of what they're looking at. So if I put this executable in Resource Hacker, we can see it's got a couple of icons stored in it. It does have the definition for a dialog box stored in it. So some text is stored in here as well. There's just stuff in here. And this is particularly stuff that they've decided to store in this standardized format. The important thing to note is that we can drag random programs in here and we can see all sorts of goodies. I mean, this is just some of the best stuff. Like, there's the start menu right there. We just found that. All we did is drag explorer.exe in here, and there you go, that's it. We've got a bunch of icons for, I think, the taskbar and start menu customization screens. We've got, like, the side of the start menu in pretty much every different, like, edition of Windows 2000. Really crazy stuff. Remember when we didn't know where this was in XP? Well, here it is in Windows 2000. Look at that. It's just right there. And for someone like me, when you see this, your immediate response is to dive into the System32 folder and just start throwing shit in here. What about calc, right? Oh, calc, we got some icons. Look at that calc icon. Wow, it's right there. That's the original. Got some menus, dialogues. Look at that. That's how calculator works. It's just a Windows dialog with a bunch of buttons on it. There you go. CD player? Sure, it's got an AVI in it. What even... Look at that, it's got look at that animation. So I was doing this one day, and I had made it to a particular file, NTOS kernel. I don't know if it's quite correct to say that this is the Windows NT kernel, but it is true that this file is loaded very, very early in startup, and is pretty important. Now, as we have seen from previous versions of Windows, things that are loaded early on startup and are very important for Windows probably have boot screens in them. So let's just check it out, right? I got some bitmaps, we got one, and wouldn't you know it, it's right there. So basically, the story for me discovering this is I got kind of lucky. As I said, you know, you might be able to put 2 and 2 together and guess that if I was a bitmap, maybe that's where I would be hiding. But I'll take it, because in Resource Hacker, our job for replacing bitmaps becomes extremely easy. All we need to do is just right-click on it and replace it, and then we can find a new bitmap. There's our classic original Aegis of Rodan image. Just click replace. Now, you do have to make sure when you're doing this that you are still loading the same format of bitmap. Like if I put a PNG file in here, for instance, don't think it would work, but this one should be of the right format. And there it is. And this animation, this scrolling animation, is just done by moving the pixels around, so it totally works on this boot screen as well. And it's just that easy. We didn't even have to do any hex editing or anything like that. Quick, simple UI to just replace a file. So we've pretty much figured this one out, but I do still have a few questions. I do want to ask if we can change the colors that we're using like we could in Windows 3. Now if I open the original bitmap here in GIMP, you will see that we do have a small color table. It's only 16 colors. Can we change what those colors are? Can we use a different set of 16? And I also want to know, can we change the resolution? Well, let's find out. First thing that we're going to look at is, can we use a bitmap that looks like this? And we're still using only 16 colors, but they're obviously a different 16 colors. Lots of greens and pinks, and it looks pretty good, honestly, for only 16 colors. So I would love to have this be my Windows 2000 boot screen, and fingers crossed. And it turns out that Windows is totally happy for you to use a different set of 16 colors, just like Windows 3.1. So as I said, I also wanted to test a different resolution bitmap, so I have this one as well, which is just the other one cropped. It's taller than it is wide. It's a very weird resolution. Anything bad happen? Well, I guess depending on your definition of bad, it does work though, technically. So we've been through a lot of versions of Windows. We went through all the DOS-based Windows. We went through Windows 2000, and the one right after Windows 2000, well, that's bringing us full circle. We're coming straight back to where it all started in Windows XP. We've been through a lot. We've been through quite a bit. I'm pretty confident at this point we have the tools and we have the expertise to figure out how to replace this. I think we can do it. Gosh, shut up. Alright, XP, let's crack you open, sell you for parts. Here we have Windows XP on the operating table, and since Windows XP is actually very similar to Windows 2000, we're going to go straight to Windows System 32. So let's throw that bad boy into Resource Hacker, open up those bitmaps, click on that first one, and it's totally black. So I was initially put off of NTOS kernel, thinking that maybe they moved it somewhere else. But this is just a little bit too promising, just like we saw with Win.com in Windows 3. Like, it's just a little bit too obvious that it's supposed to be here. I mean, look at the size of this. It's 640 by 480, which was the same as what was used in Windows 2000. So here's the bitmap itself. You can see totally black, 640 by 480. Though it's 14 kilobytes. Would a totally black bitmap that is compressed be 14 kilobytes? Yeah, that's sort of interesting, isn't it? Like, this is not what you would expect to see out of a blank bitmap, is it? What is all this data? The only reasonable explanation for what's going on here is that the image is actually there, the structure of the image is there, but we've just decided to paint everything black. Let's double check with the BMP file format article here to find where our color table would be. Let's see if we can find this out. So the color table or palette occurs in the BMP image file directly after the BMP file header, the DIB header, and after the optional 3 or 4 bit masks of the blah 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 2, 4, 6, 8, 10, and that should leave us around here. Okay, so that means that this is the section of the bitmap that defines the color table. Why don't we just, let's just define our own color table real quick with some very intentional and advanced artistry. All right, things have definitely changed. The boot graphic is in there. It's just that the color table is set to a bunch of zeros. The question you're probably asking yourself is, why? Why would they do something like that? Why would they make the color table all black so that the image appears completely blank? Is it just to throw off people like me from figuring out where the actual bitmap is? It did almost work. So what I decided to do was take this fucked up version with the custom color map and just replace the bitmap with that and see what happens. Should probably have ejected the CD. Now that's sort of interesting. So you could see that there's a moment there where it was loading the custom color map version, but then it goes completely blank before it does the fade in. And I think that that fade in is probably the answer why the bitmap has a color table like that. I think what is going on, they need it to be completely black for that split second where the fade in hasn't started yet. And then once they start fading it in, we're actually going to see it a second time now as I'm explaining this. Yep, it loads in with the bogus color table, then it does the fade in. So I think they wanted it to be completely black so that when it was loading, you didn't see it before it started fading in, if that makes sense. Now, this actually has some implications. In every single bitmap we've seen thus far, the color table in it has been respected. But no longer is that the case. As you saw, even though we totally replaced the color table, it actually still eventually fixed itself with the correct colors, which means those colors are being stored somewhere else. And that's pretty interesting. I did decide to just go ahead and make a drawing to, replace the bitmap with that used the original colors, because I figured, no matter what, that's probably going to work. Very nice. God damn it. So that works, but unfortunately, that leaves us in a situation where if we wanted to customize our Windows XP boot experience, we are forced to use the same colors. We need to find out where that color table actually is. NTOS kernel is probably a pretty good place to start, and the first lazy idea that I had was I took a screenshot of the Windows boot screen when it was fully faded in so that I could get the exact colors that end up being used, and I just took this right here. So let's search for those values, and we don't get anything. Well, okay, maybe we should search for them in the reverse order. Sometimes Windows likes to store BGRA instead of RGBA, and that doesn't work, and I'm totally out of ideas. At this point, really, I was thinking I needed to Google some of this. I was betting that Google would not have the answers for how obscure that this question is, and I really could use any pointers. This was pretty much the only really relevant result. If we scroll down, we actually start seeing some things that align with stuff we've seen before. Of course, this means that the boot screen needed to display more than 16 colors in total, and in this the poster is referring to the fade-in animation. And that is true. If you were fading in this screen from black, you would need more than 16 colors to display all the shades of the in-between. So the enumeration of colors was moved outside the bitmap, and its color palette was changed to be all black, which causes Resource Hacker and any other software working with the bitmap's own color palette to just display a black picture. Well, hey, that's pretty accurate to what we've seen in the actual release of Windows XP. Now comes this little mystery. The color palette isn't present in the bitmap since build 2419. Now that's not super interesting to us, but it doesn't seem to be in NTOS kernel either until build 2481 with the RTM boot screen. So this to me seems to suggest the color table actually is in NTOS kernel somewhere, and even though the question that this poster is asking is not quite what we're after, I did be sure to look at all of the replies to see if there was any other leads I could follow, and I saw this post eventually, which gave me something of an idea. I don't know if this is code from a build of Whistler, or if this is maybe the leaked XP code from a while ago. They do show us that somewhere, supposedly in the Windows source code, they are just defining this color table as a regular C array. The compiler has to put this data somewhere in the finished executable. So without really knowing too much what I was doing, I decided to open NTOS kernel with a CFF Explorer. And I went down to section headers here, and I looked for a section that I thought sort of reminded me of things that I learned about at one point in my computer science classes, and one of those was .data. Why don't we take a look at what's at this offset in the hex editor? You can see a bunch of entries in pairs of 3, so that's kind of promising for looking at a color table, right? And I'm thinking, you know, maybe some of this is a color table, but how would I really tell? Then I had another idea. If I'm working off of these assumptions that there's some color table data compiled into that part of the executable, these numbers should match up perfectly, right? Like, these should be the numbers. Maybe my screenshot was a bit flawed. Maybe it didn't quite get the right number. So maybe I'll just take one of these pairs here, like 21, 26, 32, these 3 hex values, and maybe they'll show up somewhere. What do you know? They're right there! And that does sort of match. If we assume that this 000 is the beginning of the color table, that does match. See what's next? We got 70, 70, 70, and then over here's 46, 46, 46. I bet you if we turn 70 into a hex number, it's 46. What do you know? It is. I think we may have found the color table, but there's really only one way to know for sure. Alright everybody, let's launch with our custom color table. Let's see it. Alright. Now that's what I'm talking about. Shut the f***! And you know what this means? This means we can use any set of colors we want for the Windows XP boot screen. This was all about figuring out how to replace the boot screen on XP, and we did about as good of a job as I think we could have. We figured out everything, even how to get it to work with our own colors. So where do we go from here? Well, I was originally going to continue this video by going to every version of Windows, but Windows Vista threw me a bit of a roadblock. Let's go ahead and check out Windows Vista like we would any other version of Windows here, but we actually start with something that is sort of similar. We have a black fade-in, and we have a little spinner with some colorful bars. Oh my god. Well, there it is. There's the orb. So you get this little XP-ish spinner loader, and then a little flashy orb comes on screen, and then the login noise comes up, delayed by about 5 seconds. Here we are in the Windows Vista disk, and we're just going to take a quick look around here. First thing that we're going to do is move right on over to NTOS kernel and see if we can strike gold again by just looking for that same bitmap in that same place. And if we do this, we will find that indeed there is another completely blank 640 by 480 bitmap stuck in here. Now, I will just save us a bunch of time and let you know that this is exactly the same, a lot like the 98 to 95 jump. This is the same technology, it's even the same color palette. So we can even just replace this with our XP boot screen and be good to go. That leaves us with one other question though. Where is the glowing orb, the second part it ends up that it's in here in authui.dll. And if we open up Resource Hacker, and we can actually see that for the first time ever, these boot resources are PNGs instead of bitmaps. I made up these nice little replacement graphics for our glowing Vista orbs, so we'll use those in our next hack. Let's move it over here. Wait for the CD thing, maybe. Uh-oh. They got my number. They finally started giving a shit that we were editing critical system files. And we can't edit NTOS kernel willy-nilly anymore. Now, we kind of can get around this if we just spam F8 every time we start up our computer and ask it to disable driver signature enforcement. If we do this, we should actually be able to see our handiwork at least. So there's our XP boot up, which is using the Vista sliders now. You can even see that the spinner is in the exact same place as it was in XP. I am believing in you less with every second. There we go. Doesn't that look great? They kind of overlay for a little bit. And then there's our delayed startup noise. There it is. And everything is good for this boot up only. Some of you are probably thinking, well, so what? This is a 15-year-old operating system after all. There's probably a pretty easy way to bypass that signature enforcement. And you might be right. The whole fun of this was reverse engineering how these bitmap formats worked and where they were and how to replace them and what the limits are. That's what this was all about. And it just doesn't feel right to turn this into a scavenger hunt for breaking Windows security. That's not really what I signed up for when I started this. And when I got to about this point, I did go through Vista and I did figure out the things we just talked about. And I did figure out a little bit of Windows 7 as well. But especially by Windows 7. At that point, people have already been making tools, really good tools that are super well documented and have open source code that go over exactly how they replace these bitmaps. So at this point, the fun has sort of run dry. This is probably a good place for this journey to come to a close. If anything that we talked about in this video left you wondering, left you hungering for nerdy, gritty details, then as I mentioned at the beginning, there is a Google Doc here that I put together while I was working on this that goes over the exact details about how all of these things work. And it basically acts as a summary of this video with a little bit of extra technical information. As well, you can always check out the IO7 thing that I made for decoding and re-encoding the Windows 9X bitmaps. This was a huge amount of work, and I'm very proud of it, even though it's not really that sophisticated. I still had a lot of fun working on this, and I hope that if you are even a little bit interested in it, you'll skim what's going on here to get a sense for what it was like to work on this and what kind of a little bit of a lost piece of Windows history, assuming that nobody else has a better document on this, like I'm assuming they don't. I will also be including in the description of the video a link to a zip that contains all of the pieces of art that I made for this project. There are not that many of them, and none of them are really that special, but I figure some of you would be interested in having them, so, go wild. They're not necessarily going to be in the correct format for replacing any boot screens, like one of them might be a PNG when it's supposed to be a bitmap, but I figure that doesn't matter too much, and besides, I gave you everything you need to know in order to do bitmap replacement if you really want in this Google Doc. And that's it! We did it! Video over! We're done! We talked about everything. This has been a very, very hard video to make. I don't know what specifically about it was so challenging, but I just could not get a script going. I could not get editing that I was happy with going. And I did try to make this like the screensaver video before, where it's well edited and it's like scripted and it's like a video essay and it's all cool and great and fancy and professional, but that just wasn't working out. I was really losing my motivation to do anything with that, and it was very challenging, and I didn't really know how to overcome that. So you get this instead. I'm glad you sticked around for the whole thing. Most people are probably asleep at this point, and this is playing into their unconscious ears, or they closed the video 15 minutes ago, or they've just completely zoned out. You made it to the end, and I really appreciate that. I'm sure that if you are still here, you are at least a little bit interested in some of this stuff, so I do hope that it was entertaining for you, and that you feel like you learned something. I was pleasantly surprised overall by how the project itself went. I was pleasantly surprised that that bitplot stuff ended up working out for Windows 1 and 2. I was pleasantly surprised that I was actually able to find all these bitmaps and they weren't stuck somewhere really obscure, like shoved into a master boot record or something. All of them turned out to be just the right difficulty for me, I think. Especially the Windows XP part. Yeah, all of it was at like an appropriate level of challenge, I would say, and that was very fortunate, serendipitous, I think. There's a lot of interesting stuff going on in the later versions of Windows, like Windows 7's is really interesting. That might happen another time. I have a feeling, though, that I'm going to take a pretty large break from doing anything boot screen related for a while, and you probably won't hear from me until the middle of next year. Maybe I'll have that screensaver follow-up video, who knows? Probably not. Until then, we'll catch you guys next time. See you later, and take care. I managed to make it through this entire hour-long video without mentioning Windows Gangster Edition a single time. Here's the mention. You can do this now.